Hi everyone, so let's continue where we left off last time. Did I solve 26? Yeah, I didn't solve 26. Okay, so let's solve 26. If A divides C and B divides C and the GCD between A and B is D, prove that AB divides CD. So yeah, just here the logic is that if we have both numbers fitting into some number, then when we multiply them out, then we must have that their multiplication fits into one of the numbers where both numbers divide, multiplied by the other structure where both numbers fits into them. And here we don't have that there's any other structures which is introduced, so we don't get a jumping behavior that we might get with numbers. So that's the main point. Yeah, so that's again it's an application of Bezout's identity. So because the GCD between A and B is D, then there is a U and a V such that A times U plus B times V is equal to D. If we multiply by C, then we get A times C times U plus B times C times V is D. We can replace one of the C's by B and the other C by A, and then we get our result. So here A times B times K, or let's just leave the K, U here, plus again A times B times RV is D times, so that's DC here, and DC, CD is the same thing. So then if you factor in AB, then you get the result. So therefore, AB divides DC. Okay. All right, so let's see the following question. It's a very interesting question. So you could also solve it by modular arithmetic. So prove that a positive integer is divisible by 3 if and only if the sum of its digits is divisible by 3. So yeah, so let's see what's going on. So any integer can be written as additions of multiples of 10. Yeah. So that means that, let's do the forward direction first. So that means that any integer can be written as 10 to the power of n multiplied by b, or let's call it an, plus 10 to the power of n minus 1 times an minus 1 plus blah 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 plus a naught. For instance, 551 is 10 times 5, and it would be, how many tens are we taking? So taking one 10 we get 50, taking another 10 we get 500. So, and then we add, we want 50 times 5, and then 10 to the power of 0 times 1. All right. So what we can do is write each 10 as just as 1 plus 9 to the an plus 10, so that would be another 10, which is 1 plus 9 to the power of an minus 1 plus blah 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 a naught. Each of the 9s here is a multiple of 10 of 3. So each of the 9 is a multiple of 3. So we can write them like that. So we have 1 plus 3 times kn to reach, or 3 times 3 to the n an plus all the way to a naught, where we have 1 plus 3 times 3 raised to the certain power. So this should be n minus 1. And then what we want to establish is that each of the digits is divisible by 3. So we can use the binomial binomial formula. But instead of using the binomial formula, let's reason our way about it. So here you have 1 plus 3 to the power of 3, not 3 to the power of 2, which is a multiple of 3. So you have 1 plus a multiple of 3, and all of that raised to the power of n. So then once we expand that out, you will get the terms an all the way. So because we're guaranteed to have, when we expand this out, we're guaranteed to get an plus all the way to a naught, and then plus some mixed terms, where those mixed terms have a multiple of 3 in them. So then plus 3 multiplied by some k, or let's just do p. So then if 3 divides a, then we must have, by the uniqueness of the division algorithm, we must have that an all the way to a naught would have to be 0, unless, because then if they give a remainder, because that's the division algorithm. The division algorithm tells you that if we divide a by 3, then we're guaranteed to find a quotient as well as a remainder, and those things are unique. So here we have expressed a in terms of a multiple of p. So then we cannot get that those an plus blah 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 a naught, they cannot add up to things that are not a multiple of 3, because if it's bigger than 3, you can collect the things that are fits into 3, and you can get the remainder. But then that remainder must be unique, right? So then in order for this to be because we started out that it's divisible by 3, then we must have that this addition is divisible by 3 as a result. So that's the core reason. So by the division algorithm, we must have that 3 divides an to a naught. Let's just expand that detail out. So since 3, since we started out with, since 3 divides a, so by the division algorithm, we must have that a is equal to 3 times, let's use s plus r, where r is in between 0 and 3. Yeah, and that also A can be expressed as a multiple of 3. So 3, so you have 3s plus r, which is equal to 3 times k plus or is p, 3 times p plus a naught plus all the way to an, where r is 0. So by assumption, r is equal to 0. So then here a naught plus an must be divisible by 0, because otherwise apply the division algorithm with 3. Apply division algorithm with 3, and you get that 3 times alpha plus r is equal to a naught plus an. So therefore a is 3 times s, which is 3p plus 3 alpha plus r, which is just 3p plus alpha plus r. So r is equal to 0 by the uniqueness of the division algorithm. So going in the other direction is trivial, because if we express every term as a multiple of 3, then using the star here, we get that a is a multiple of 3 by the fact of double star. Yeah. Alright, I don't like to use trivial, so let's just say easy. Alright, I'll end the video here. See you guys.